Hello and welcome to a new season of Science Radio. We're back after a summer break with an interview of Dr. Venkatraman Ramakrishnan, winner of the 2009 Nobel Prize in Chemistry. Dr. Ramakrishnan, whose parents are both eminent scientists, is more popularly known for his work in structural biology. However, he began his career in physics. He has a BSc in physics from MSU Baroda and a PhD in physics from Ohio University. He currently works at the Medical Research Council's Laboratory of Molecular Biology in Cambridge. We talked to him about life, science, and the Nobel Prize.
In the early stages, it wasn't clear that I wanted to be a scientist. I wasn't sure I wanted to go into anything technical. The work I did was to help solve the structure of the ribosome.
This is Science Radio on Vidyavani 107.4. I caught up with Dr. Ramakrishnan at the ISER Pune Media Center. The first question I would like to ask you is what attracted you towards science? Did you always know you wanted to be a scientist?
It's hard to say because my parents were scientists. In the early stages, it wasn't clear that I wanted to be a scientist. I wasn't sure I wanted to go into anything technical. And then I became interested in science and mathematics due to a teacher in high school. But even after that, I wasn't sure whether I wanted to do engineering or medicine or basic science. And I think in some ways the decision was made for me by a variety of factors. One is that in those days you did pre-science after high school. They didn't have this +2. So you had to finish high school and then go to pre-science. And after that you split off into engineering, medicine, or a BSc course. I applied to the IIT institutes. In those days, the IITs only had engineering. I also took at this time the National Science Talent Search exam, which was a very prestigious thing in its day. I got that, and that scholarship, in fact, that whole program was only for basic science. So I sort of thought of it as a sign that I should do basic science. And at the same time, the physics department at my university had some very forward-looking professors who had modernized the physics course. So the combination of all these things meant that I started studying physics for my undergraduate.
So your journey in science began with physics, but you're more well known for your contributions to structural biology. How did you switch between these two fields?
When I was in graduate school in physics, at some point I stopped being interested in the problem I was working on. And it was very clear that I would not make it as a first-rate physicist. That was one reason. That's sort of a negative reason. The other reason was that I would read about all these huge advances in biology. So it struck me that, this was a much more exciting way of spending one's life than doing some sort of second-rate work, in a mature discipline. And so I did that. And actually, I knew that many physicists had made that transition. Francis Crick is a most famous example, but I knew this sort of transition was possible. And so that's what I did.
Was it difficult switching between the two fields?
I made it easier by going to graduate school again. Sometimes you have to step backwards in order to go forward again. And I think if I had gone straight into some postdoc in biophysics or some biological lab, in fact, a couple of labs offered me postdocs and I refused. Because then you would only learn that very narrow area and you wouldn't have the broad biological background even to understand that area. And I think people who do that end up not being so broad. Anyway, I didn't know undergraduate biology, so I had to take undergraduate biochemistry, genetics, cell biology. So I did all that while I was doing my initial graduate courses as well. So the first year was really pretty intense, and I had a newly born kid, an older daughter, and we had just moved to California. But, I was also young. When you're young, you don't worry as much. You just sort of take things as they come.
You were awarded the Nobel Prize in Chemistry for studies of the structure and function of the ribosome. Could you tell our listeners more about the research that led to the prize?
The work I did was to help solve the structure of the ribosome along with others. What the ribosome is a large molecular machine. It consists of 500,000 atoms or more. And this machine takes the information in our genes and makes the protein that's specified by that gene. So proteins are long polymers. They're long chains of amino acids. And there are 20 types of amino acids. And the order of the amino acids that make up the protein is specified by the information in our genes. And so the ribosome is a machine that reads that information and based on that information stitches together the appropriate protein chain. And there are thousands of genes in every cell which code for thousands of proteins, all of which have lots of different functions. It's absolutely essential to life as we know it. It's one of the oldest molecules around, so that's why it was important.
You shared the Nobel Prize with Thomas Stites and Ada Yonath. Did their work affect yours in any way?
Yes, and well, we were competitors, constantly aware of what each other is doing. Techniques that one person has developed are quickly adopted by the others. And so in that sense, we were not sort of willing collaborators, but we were indirect collaborators, if you like.
How did you react when you first were told that you had won the prize?
I was rather surprised because there were several reasons why I didn't expect it. Not because the ribosome wasn't important, but I was surprised to be included as one of the three. And not even because I thought our work was, that any worse than any of the others. But there were reasons why I thought I would not be one of the three. I was fairly surprised.
Your initial work focused, as you said, on the determination of the structure of the ribosome. But your later work has moved towards the translation of mRNA to protein. Could you tell us?
That's what the ribosome does. It translates mRNA contains the genetic message, and the ribosome reads the mRNA and makes the protein. But you have to think of this as a large, complicated, you can think of it as a molecular machine, if you like, although some people don't like that term. But if you want to understand how it works, just solving the structure of an empty ribosome isn't going to tell you how it works. For instance, if you were from Mars and you came here and looked at the details of a car, that might not tell you how a car works. In order to understand how a car works, you would actually have to see it working. You would have to see the spark plugs firing and the pistons being pushed down and engaging a crankshaft, and you'd see how gasoline was injected at the right stages and so on. So it's a little bit like that. We're still not finished, but what we spent the years from 2000 onwards doing was to try and trap the ribosome at different stages along the process. And that would allow us to see how the ribosome gets from step A to step B to step C, and in a way try to understand how this complicated molecule works.
This is Science Radio on Vidyavani 107.4. We are in conversation with Dr. Venkatraman Ramakrishnan, winner of the 2009 Nobel Prize in Chemistry. You're also a major advocate for the judicial use of antibiotic and antimicrobial drugs. How did you get involved in this effort?
Very indirectly, because many of the clinically important antibiotics target the ribosome. And so once we had solved the structure of the ribosomes, we could also understand how these antibiotics bound to it. And that led to companies being interested in using these structures for developing new antibiotics. And that led me to become involved, first with a small startup company in Cambridge, which then got bought a couple of times and lost interest in the ribosome. And then with a company founded by Tom Stites and Peter Moore and their colleagues at Yale. And working with these companies made me realize how difficult it was to develop any useful new compound. And then when I looked into it, I also realized how expensive it was and how long a process it was. I mean, this company has existed for over 10 years, but there's no drug on the market yet. And so this shows you what a long and expensive process in development of a new antibiotic is. And it's why there are so few new antibiotics. There are not that many. That made me realize abuse of antibiotics is actually terrible because we have all these useful antibiotics, and if we render them useless, then we're hurting ourselves because it's not like we're going to be able to flick a switch and get a new antibiotic.
So you have worked in several labs across the US and the UK. Did shifting around impact your work?
I only moved because I felt I had to. You have to do what's best for your work. For instance, after Yale, I went to a national lab, which turned out to be a disaster, and I had to leave after 15 months. In fact, only 2 or 3 months after I got there, I was already looking for a job because I knew I couldn't do my work there. And so I could have had a reasonable life there, but I wouldn't have been able to do the sort of work I wanted. And then I went to Brookhaven National Lab, and I was very happy there, but the organization that administers the labs kept changing its priorities and policies, and it was clear that I would be better off going to a good university. And so I went to the University of Utah. And then when I started working on whole ribosomes, I wanted to be in an environment where I would have very stable support because this was potentially a very difficult problem. And I also wanted to be surrounded by people who were experts in pushing structural biology to its limits. And so I went to the MRC lab of molecular biology, which is very world famous for structural biology, precisely for that reason. And again, I took a 40% pay cut, but I did it because I felt that was the best place for me to try and concentrate on solving the structure of the ribosome. So in each case, if you feel that to get to the next step you have to move, sometimes you have to move.
What are your hopes for the future of science in general and science in India in particular?
It's difficult everywhere because, for instance, in US, the science budget is under attack. It's harder and harder to get grants. In fact, last year's Nobel Laureate said that, one of them, Jim Rothman, says he tells all his foreign postdocs to go back and leave the US. In Britain, fortunately, they didn't really cut the science budget. They froze it. That itself was a big vote of support for science. So actually, I think the UK has turned out to be a very good place for science. And in fact, many Americans are now moving to the UK for that reason. But of course, the UK has its own economic problems. And until those problems are solved, it's going to be a problem. I think in India, science funding improved a lot over the last 20 years. And creating really new institutes like the ICER here is a good move because these institutions have the opportunity to get away from some of the hierarchical, stifling traditions of certain older Indian institutions and create something where people are given the freedom to do their work. There are quite a few Indian institutes which I think are doing good work, and the hope is in time they will also do great work. There is a difference between doing good work and really world-leading work. So I would be optimistic, but there is one problem, and that is science is expensive. It's not as expensive as defense or, various social programs. So in terms of the fraction of the budget, it's not very much. And so governments really shouldn't bother cutting science because it doesn't cost much. And if you cut it, you disrupt a long process because it takes a long time to train people. And if these people leave science, you have to find new people and train them all over again. So it's a waste of time and money to cut science. Because scientists are not very well organized lobby, often, in bad times, governments tend to cut science.
Could you tell us about your interests outside of science?
Like everybody else, I have various interests. I like music, literature, hiking, bicycling. I like going to movies.
Finally, do you have any words of advice for the students and the young scientists listening to our program?
I would say, the facilities are there to do really very good work in the best places in India. I think students should look beyond doing the next experiment and start asking what is the really interesting question in their field and try to think how they could go about attacking it. You can't just answer the question all in one go, but you can sort of think of it as climbing a large mountain. But if you keep the goal in mind, each stage along the path is getting you closer to that goal. I think students should be encouraged to think and ask why they're doing something. They should always be asking why I'm spending part of my life on this. Why should I be doing this?
Thank you, sir, for your time. And I hope we can catch up with you on your next visit to Pune. With this, we come to the end of today's episode. Tune in again next week for another episode of Science Radio. We would love to hear from you. Do write to us. Our email ID is radioiserpune@gmail.com. That is radio, IISER, Pune @gmail.com. This is your host, Adithya, signing off.